Hello everyone. Thank you for having me here to do my presentation. I prefer to talk about my presentation, color recognition, sorting, counting, automa- automation, control system. I'm a Hong Yu. I'm from Fitchburg State University, Engineering Technology Department. So, as we know, the control systems has influenced the aspects of our life such as artificial intelligence, such as the remote medical and manufacturing. So for all these control systems, we know knowing how to manipulate the data from the temperature, pressure, and the humidities to automation control system can assist with innovation and improve quality of human life. So that means that all the data we can use for our control systems. So the especially in the plastic manufacturing of industry, there is a need of automated control system that can recognize color, sorting, counting, and the sequential control process. Since the certain quantities of color palettes mixed into the batch in order to produce desired colorful parts. So as we know, in the plastic manufacturing, we are injected some products where that's what desired colorful parts. So they should mix together. So we should have a sensor detect it and also where accounted. Then we can go to sequential control process next step. Okay, that's we know that. So here I give example. That's I give to you some illustration, look like image, and also the remote station. So this one that's in plastic manufacturing. So we have a different color. We have a red, blue, and green. So after that, we are give to mix together, then we'll go to products. So a color recognition device, such as a red, green, blue color detector, so should design it. And also we designed it on, when we designed this device, it should on the principle of energy harvest, corresponding accurate, well measured reflect the light energy in the automation control system. So that once so when we designed the detector, we should follow the principle of energy harvest. So that's for our device when we design the. So when you talk about the energy harvest, so for this case, we are talking about the light to analog voltage color sensor. So this sensor is comprised of an array of photodiodes and photoresistors and an integrated voltage conversion circuit. So second, the most practical analog output color sensors incorporated a transmission impedance amplifier and provide the voltage output at least. So that one say the light, we always talk about the light. So we are use the photo detector. So this photo detector, how to detect it? That's a light we call the energy harvester. Reflection may be different. So that's principle. At the same time, we wanted the output should be from the device should be the analog output. Okay, and also when we talk about the RGB circuit, we are mixed inside. They have a color shift. So the derivation voltages due to the red, the green, blue shift in color recognition, sorting and counting automation control system is as an analog signal input of controller. So after get the signal and coming, they will go to controller. Due to reflected light properties. So what reflect the property? Because they have a different color. We are talk about temporary. We talk about RGB. So here, I give to example for about reflection sensor and also transmission sensor in emulations. Okay, so for here we have one. The LED look like a source. Okay, look like a source. They have energy. They have energy over there. So that's for first. So and also after get reflection, the energy may be different, right? So we have a red object, green object, and blue object. So we use the same sensor over there. So maybe the energy, the the energy is different. So that's we know that. So that's only one LED over there. This one we call RGB reflection sensory. Another one that's transmission sensory. That means that behind the LED, that's a sensor behind the filters. Okay, the sources on the left side. So this one still can do that, but this one we should go through the filter, the color filter. That's red, green, and blue. So for us, we'll talk about it reflective sensory for today. So objective, continue. So the powering LED energy harvest for the various commercially available vertical cells will determine the most suitable photoresistors with respected voltage gain and the current derivability. So all this harvest engineering is studied in the circuit for the power LED array. Okay. And the power consumptions of presented LED is optimized by using response surface methodologies with respect to following input parameters. So we're used RSM, we call response surface methodologies. And also the input parameter, we use the voltages with respect to the consuming power and reflect distance. Okay, reflect distance. So that's for this case, where optimize this reflect distance and also for the voltages. So I will introduce a little bit RSM. So RSM, that's a response surface methodologies. It's a set of technologies from mathematics and statistics used for the empirical model building and the model optimizations. The optimization proposal optimal input parameter for the minimum power consumptions and operating distance that presented a compromise between the aforementioned parameters in the reference to the input variable. So that means that we can adjust it, we can calibrate, make sure that is good optimizations exactly in the manufacturing, and it's very important. So in this project, the related work on the LED energy harvester or power assumptions the circuit and optimizing distance that haven't been optimized. That's how I say that. So since output of energy harvester is not directly suited for the circuit, management the voltages of current circuit is requested. So the voltage until should handle the very low fitting power and adapt to the output of a load. Okay, we wanted all the energy harvested, and also we built the manage and the voltage or current circuit for the device. So the value treated as input parameter, well as the model response the parameter is power assumption represented as voltage. The voltage will be measured and also evaluated by HMI system interface, and also that's for SCADA. So HMI, that means the human machine interface. At the same time, SCADA, that means supervisory control and the data acquisitions. So that one, so especially in plastic manufacturing, there is a need for the system with the color detector that automatically recognize red, green, blue colors, sequentially control manufacturing process. Meanwhile, calculating a weight, cost, and quantities for the color parts or merchandise. Therefore, a system with color detector circuit has been designed. It will recognize sword counting red, green, blue color with designed device. At the same time, integrated the color detector to the HMI automatically control systems with SCADA software. The system involves modern, sophisticated ways the automations, the control, and the monitoring. So that's for the system description. So for the color recognition, sorting, and counting automations, the control system included 3 parts. So first one we call design the device. This device that's for the harvest circuit. That means that we are measured by the LG. We'll talk about RGB color sensor. Then second, we go to the microcontroller or PLC interface component. And the third, we go to SCADA or some supervisor control software we call SCADA to monitor and adjust the microcontroller, the interface or PLC interface. Okay, so in the manufacturing we always use the PLC interface. So since RGB color have different reflection properties, so absorptions, the minimization and effective energies, the approaches can be utilized to quantify in voltages, and after that, then to design the color recognition device, right? Because the absorptions is different after the reflection, the RGB color. So it detected the different color reflecting energy consumptions if a narrow band light source are optimized for the color object reflection, while preserve the color appearance. There is a large variance in the absorptions value due to the difference in the spectral reflectance the characteristic. So the main characteristic of design the color recognition will be enhanced. Okay, will be enhance the reflective energy sensory. So that's we develop. So the color recognition developer, we get the two now. So we get two LED and the gold sensor. So this time we have a spectrum coming. So for this one, the optimization harmonic source is needed. So after get this one, so two LED are chosen as a light source now. That's developer object put the same red and color and the green color and the blue color. So because harmonic source coming, the obtain the distance also represented as compressed optimal input parameters. Okay, to measure spectral quantities of power consumptions with a different distance. The voltages are calculated by adding intensities of the individual wavelengths with each range. So we can see that. So we have a two LED, and in the sensor we call the photodiode or photoresist over there. So different, we put the distance that's half inches. Okay, totally half inches for D, and also we have a distance reflected light difference. They have a harmonic. So have a harmonic source coming. So here, because the intensity is different, so this I is different. So for this case, red, green, and the blue measure the voltages in the circuit. Since the circuit we use the I pair, that's 24 volts. Okay, so that's we say that blue they have a percentages. What means percentages? That means the density, intensity is different. So I will prove that. Okay, so we can measure the I blue, green, and the red. Okay, so here we are designed the sensor device. Okay, we have this one. We have a voltage come here. So we have voltage come here, and also we have capacitors. So we have two LED, and also we have photoresistor over there, and the output is here. We can calibrate this one. That's we talk about put a range or just like a calibrate for the sensitive. So here, that's what we did. So we have a two over there. We have a solid and the photodiode and the photoresistor over there. So after that, we put over there. So after we put over there, we designed this one. So that's the circuit we did. So after that, so that's the data. So from this data, we can see that. So we have put a different, what's mean different D. So put the different D on the top, objective or target on the top. We put the red color, we put the green color, we put the blue color stuff and the covered on the top. So we can see how to change it. So and the distance put a different millimeters, and another one put 10 millimeters. We can see that they changed it a little bit. They changed a little bit, and also we changed we use the target, the color. We use the code at CC 3300. That's for red, and the 009900 for the green, and the 000CC for the blue. We chose this the code, the color code for that. Then we can define it. So we can see that that's blue color changed a little bit, only a 10 to the 15 millivolt. Okay, but the green they changed a lot. They go to 200, 180, 90, look like that. Actually, I remember that. And also red color, they also have almost 120 different over there. So we go this one because the intensities that changed, the current changed. So and also different color observations, all the consumptions that is different. We call energy harvest, right? So put all this one, we can see that. And we did this one, I get different. Okay, that's almost same. I put the 1 millimeter and the 10 millimeter. We can see what's happened. So how to do the 10 millimeter? How to do 1 millimeter? We put the target. I measured this one and on the top. So we can see that. So at the same time, you can extend it, the tube. Okay, extend the tube. You can see that. We can measure. So after that, now another thing, because we talk about the percentage, or you say that's equation, we can talk about this one. So we can put the intensities or percentages over there. So we are use the different color. That's FF9999 for the red, the color code, and the 99 FF99 for the green, and then 66 CCFF for the blue. So a little bit light. So we can compare it. and the distance we put 6 millimeters. So we can say regular. What's mean regular? That's we use this regular color. So after that, and we put the light. Did you see that? This one almost same because we didn't put any reflected over there. Let's prove that. That's great. But for the color, blue color, you see they change it. And also green color they change it, and also red color change it. That means the color code changes. That's reflection energy or absorptions, or you say consumptions is different now. So we can measure this one. Because this one is different, the red, blue, do you see that? Red, blue is different. So we are do this one, we can say, okay, this one a little bit different now. You see that? A little bit still different. You see, for each one, they're still different. This one is 3.7, 3.6, and 4.0. So that's all different. So in future, we can use the impedance to amplify to, amplify it. So after we get this device, so next step, we'll talk about HMI automotive control system. So HMI, the HMI include the PLC and the SCADA as hardware and the software. It compatible and performing much more complex tasks with other manufacturing facility. The following at the show, did you see that? We put the device, we put the relay, we put the PLC, we have SCADA over there. This one, that's PLC code. So SCADA, what's SCADA? SCADA is the central system used the monitoring and the running planned process. SCADA is used in the conjunctions with other devices. It's typically software installed on the computer, and one of its major functions is to act as interface with industry machine or other HMI. The SCADAs communicated with the PLC through the internet protocol, accessing IP address remotely from anywhere there is an internet access. It allows the users to track information coming from equipment, they enter comments and make changes to the program. So, and also, since each color has its value range, there is a specific colors value range by added and subtract range. That's I talk calibrated over there. It sensitively can be adjusted from SCADA scan and the scan screen also. So PLC has a 3 channel to recognize and sort and account for the SCADA. Okay. There is a system have a scan time adjusted. We can scan it each maybe. I put 3 seconds. We do that as I remember that scanned it. Okay. So that's scan the times is duration of output. Okay, for that one. So and the analog digital converted also for and by the PLC. The converted measure the voltages to design the sensor device into a digital voltage, digital date. The digital values is compared to setting value range. Set up putting a color put on the RGB sensor device recording on the SCADA screen. So that's where SCADA screen. We put the blue, we put the green, we put the red. So we can account it. We use this software we call the SCADA. Okay. So after that, they all can remote it by the workstations. That's also they monitor the weight of material, the sort, and the count. That's where we can see that. So summary, the review on the significant RGB reflected light to the color recognition, sorting, counting, automation, control system. The color reflect the lights and experimental verification of LED energy harvest applied it to the plastic manufacturing. The RGB chroma question generally used in the effective measure have been introduced and experimental. The combinations of the distance of reflected light and the RGB color is beneficial for the aim of the effective measuring in color precision and also precisions. So that's my presentations and maybe of future work over there. We'll talk about it later, how to put emergency and if different. That's another thing. Okay. So any questions? And I prefer to answer to you. Question and answer. I prefer to answer to you. Okay. Thank you. Thank you. I stop the record.